Hello and welcome to week 2 of this introduction to big data as part of the BSc program. So in this week we will go deep into the cloud set of technologies. We will actually be spending time on what are the different facets of the cloud, which makes it extremely attractive for big data practitioners such as yourselves. The ability to write programs at very large scale is immensely helped by certain facets, certain features of the cloud. We will look at how they evolved. But even more importantly, we will look at how cloud itself came to be, right? And why, as programmers who go into a world which is cloud first, you have to be aware of this foundational architectural paradigm of software, which is called as cloud native. So by the end of this week, you would not only be familiar with what cloud is, but also be familiar with how to write cloud native programs and where exactly data and data engineering and data science fits into this landscape of cloud native software. So let's start. Let's go into the history a bit. As we did with MapReduce and big data, we would spend a bit of time talking about the context of the cloud and how it evolved. So imagine as though you had time on the x-axis, right? That's in the bottom half of the screen, and leading up to where we are today, logically, there's been a bunch of different, evolutions that has happened to the way IT and software has been created. So back in the day when specialized software were first built, I'm talking 60s and 1960s, 1970s, the kind of hardware that was required for running those software were special in the sense that you needed to engineer that hardware and needed to build that hardware in the sense of being able to run only those kinds of programs in a way that was special. So that happened at that time using what came to be known as appliances, and the kind of problem statements those appliances were solving for with specialized software that was built internally within those appliances were catering to specific business problem statements, right? They were not general purpose, they were highly specialized pieces of equipment. So the best example that comes to mind from back in the day was ATM machines. So in fact, most of us today probably do not even use ATM machines regularly because we just use things like UPI. But back in the day, when ATM machines were revolutionary, the reason why they were revolutionary is because you didn't need to go to a branch of a bank anymore to withdraw cash. But even more interestingly, you had a machine that could reason about cash, right? That could reason about what notes were provided by you as part of a deposit and ascertain that those notes were not fraudulent. And then in return, if you needed to get notes out, if you needed to get cash out, it had mechanisms to understand what denominations, how many numbers were necessary to meet your requirement, and then be able to service that requirement by disbursing cash. And this disbursal also required certain mechanical levers to be pulled, some certain boxes to be opened, right? So that allowed you to put your hand in and withdraw the cash, etc. And it also had mechanisms for authenticating who you were as a person, as an identity. So a lot of things went into creation of those ATM machines, and those were very specially designed because you needed to take care of security, hacking. You needed to cater to scenarios where the ATMs were deployed in very far-flung places which didn't have frequent human presence. You had to assume certain things about the network connectivity. In fact, in most cases, the ATM machines were wired up to the bank's own network using dedicated cable, right? Dedicated network connections, not the wide area network, not the public internet that we see today. Okay, that's one example. The other example of an appliance that I want to pick up as an analogy is the world of home appliances, right? nobody thinks of home appliances as running software, but you've seen so many advertisements of late of smart machines, smart refrigerators, smart ACs and things like that. They're smart only because they have some programmable software that's available within them, right? It's not that they are genuinely smart and thinking about problem statements like you do. But even before the connotation of smart came into marketing the home appliances, back in the day, home appliances were indeed equally smart, right? If not having the slick marketing budgets, they were programmable. They were having the ability to take inputs from users, and they had ability to regulate themselves in terms of functioning. So one of the best examples here was a thermostat, right? A thermostat was a piece of equipment which you installed in a home, especially in colder climates, and you could control the temperature that you desired using a setting, but then the thermostat itself regulated how much heat and how much cold it dispersed to the entire house, and sometimes it got it approximately right, but it was a case of a specialized appliance which had its own mechanism to control read a temperature and then have some kind of a programming to control how much heat or how much cold to provide to that household, usually heat. Okay, so two examples of appliances that we saw. Now, what happened over a period of time was that the cost of the appliances, which means the cost of producing the appliance, the cost of maintaining and servicing them, was significantly high, right? And over a period of time, as the processing capability became really powerful and became cheaper, right? Mainly due to the advent of the Pentium processor, right? And even before this, the x86 processor from Intel. Basically, the advent of Silicon Valley, right? The word Silicon Valley came from that time. At the time, what ended up happening was servers, which packaged a bunch of CPU, memory, and hard disk together into boxes. They started to get shipped, and they started to become cheaper to assemble and cheaper to procure. And the servers were general purpose because the chipsets were general purpose. You could program them to run anything, right? Not just very specialized pieces of code. And as a result, new breeds of software needed to be built to operate on top of those servers. And because the chipsets were general purpose, the programming interface that the servers provided were also general purpose. And that's when C++ became popular. It became easier to write general purpose programs which could operate on a variety of different types of servers, as long as all those servers supported the same chipsets, right? And that form factor resulted in the rise of commodity hardware manufacturers like Dell as an example, HP as an example, right? So a revolution opened up because of the way that chips were standardized and general purpose and became really cheap to procure, while at the same time the processing capability just shot off through the roof. In fact, there's an unofficial rule of thumb which came to be known as the Moore's law, which effectively stated at that time that the ability to process doubled in a standard server for every 18 months or so, right? Every 2 years or some such thing, right? So much revolution was actually happening in the world of server-based computing. What this meant was the monopoly the appliances manufacturers had was breaking. So now you could write software independent of the servers, you could ship software independent of servers, and in fact you could replace software as and when you needed to, right? You could ship the server separately, you could get the softwares there, but then you could replace the software with newer forms of software, or even newer software from newer competitors. You were no longer tied to a specific competitor, rather tied to a vendor who provided software in a specific frequency. You could ship software more, you could ship newer forms, you could get it from newer players. And this meant that business problems could now be solved by completely different types of companies, right? No longer only those companies which had huge amounts of money which could maintain these appliances for you. Now, this resulted in an explosion of different types of software, and as a result, some of those software started to produce telemetry. What I mean by telemetry is some of the software started to produce data about its own functioning. So think of telemetry as exhaust, right? Just like an automobile, like a vehicle, like a two-wheeler or a four-wheeler runs, and as part of its execution, as part of its running, it consumes fuel, right? Fuel is basically, the analogy is servers here, right? It consumes fuel, and then it burns fuel with a mix of oxygen from the atmosphere in an engine, and then it propels that particular machine forward. So the analogy here, it propels the business forward, the software propels the business forward. As exhaust, the engine produces gases, right? And those gases themselves get released back out, right? And those gases are effectively exhaust from the combustion process, right? Likewise, the software, when it produces outcomes, right, that's necessary for the business to continue to be propelled forward. At the same time, it also can be made to release data as exhaust, which captures what is the current state of what is happening in that business. Like, just like you can analyze the exhaust of an automobile to understand what is the health of the engine, what is the extent of fuel mix, what is the current wear and tear that's actually happening inside. Likewise, you could analyze this data exhaust to understand what is happening inside that particular business. Is that software meeting the business needs? If not, should we have to change it, etc., etc. So what started off as data exhaust from software very quickly became critical data that's necessary to analyze. And in order to analyze that data, you had to start actually storing it. And the moment you had to store data, you had to actually have mechanisms of storing data which was structured, and that's how relational databases were created for the first time. RDBMSs were created by the likes of Oracle and IBM, and then later by Teradata, and then became open sourced over a period of time using MySQL. Sun Microsystems was one of the first to open source databases. It created MySQL for the first time, available for mass market, etc., etc. Then Postgres came about as a way as an alternative philosophy for open source databases. So all that revolution started, basically the data revolution started around the 1980s as a result of being able to look at how to optimize software, how to separate data as an exhaust from mission critical data that's necessary for analyzing how the business is performing. So notice that the need for data comes from the fact that software which is built for a specific business is already outdated the moment the business changes, right? So as businesses change, you have to go back and update the software, but it's hard to understand what is the current version of the software without analyzing the data that comes from the software. So data gets analyzed, it gets compared against what is the current state of the business. What is necessary for the business to change is then propagated back to the software as the output of data analysis, right? So that's how data became mission critical. Then that cycle of analysis started to become bigger and bigger. So data itself started to get stored in databases. Now, while this was happening, what became interesting was servers, which were essentially assembly of hardware, of CPU, memory, network, and disk. They became more and more centralized into these large players who became very good at it. Like I'm talking about the likes of Dell and HP, IBM, right? So over a period of time, it became prohibitively expensive to own these racks of servers at a particular point in time, because you not only had to procure servers for every single thing that you wanted to run as software, be it if you want to set up a web interface, you had to have a web server. If you had to have business-facing software, you had to get database servers. You have to get software application servers. You also have to get servers for running your networking, servers for running your those are dedicated servers, effectively, like routers and switches. You also have to get servers for essentially interfacing with third parties, etc., etc. So you have to start procuring racks of servers together, and not only that, you have to start renting space from data centers, because racks could not be set up in any office, so to speak, because those racks ended up creating a very high footprint on the environment. If you didn't know how to maintain it properly, you have to pay for power, you have to pay for air conditioning, cooling. You have to worry about networking those servers together, keeping all those lights on. If something goes wrong, then somebody had to worry about constantly going back to the rack and keeping the power, keeping the lights on. Or you have to pay quite a large amount of money in order to get somebody else to do it for you as a managed service. So the operation of servers became something that was quickly becoming expensive. So what ended up happening was startups which were starting their businesses for the first time, and they were very small, very nimble in size, who were wanting to stand up very quickly like a web-based business. Like I'm talking the heights of the dot-com boom back in the year 2000, just leading up to it. You have these startups which are coming and creating like fantastic innovation in very quick periods of time, but they had to then go and procure these racks of servers. Somebody had to go set up those racks in the data center, and ordering the machines from the likes of Dell and HP took like months together in terms of time. So agility in terms of servers, in terms of setting that up, became a problem compared to the speed at which the startups were necessary, were creating value, right? The speed at which the business wanted to change. And couple that with the cost of actually operating that resulted in a market opportunity that was capitalized by the advent of cloud, right? And the advent of cloud was created, the concept of cloud was created by, at that time, Salesforce, one of the up-and-coming startups at that time, which played to the problem statement of how do I make sales more effective? How do I make sales of software more efficient, right? Or sales of service products, whatever it is that you're selling. If you can, how can I make that more efficient? Salesforce started as that kind of a company, providing software that made the selling process more effective. But then very quickly they realized that people did not need to buy another machine just to run my sales software. I could run it on my own. I could run it on my data center, but allow people to rent my software, packaged together along with my hardware, along with my the cost of maintaining the rack and the power, the cooling, etc. All of that packaged together into one offering, but what the user would see is one price point, right? So they don't have to worry about any of this, and in return, I could keep charging them rent for this, right? Instead of selling them software once and keeping on maintaining it for a small fee, I could just charge them rent, just like a building owner charges rent for his building to his tenant, right? I could charge rent for this entire thing and keep charging rent forever, right? As long as the user kept coming back for the software, I'm good, right? I could just keep charging that. So this resulted in a very different shift in the way that businesses operated, but it also resulted in a very different financial model. So now a company like Salesforce could project into the future that I'll keep getting rent like this for as long as I'm the only provider of this kind of software, or this kind of a rental software for this sales application, right? So if you kept innovating, if you kept making differentiated software like this, I could just keep charging rent over over long periods of time, and that resulted in a guaranteed cash flow, and that became very attractive for certain kinds of investors to invest in. But more importantly, for the users of that software, it became very attractive because you no longer needed to rent or procure hardware anymore, right? You could just rent it directly from these cloud-based companies, and then not have to worry about it at all, right? You don't have to worry about maintenance, you don't have to worry about keeping the network cables plugged in, etc., etc. So Salesforce started this concept, like I said, but Amazon took it to a very large degree and made it super attractive for startups to engage with, right? So startups became their first clients. I remember dealing with them back in the day when I was part of a startup. It became very easy to set up my own machines. It was quite complex from a developer standpoint compared to where we are right now in terms of cloud, but nevertheless it was still easier than having to learn networking, having to learn how to cable up machines together, etc., etc. Great. So right around early 2000s, cloud started to become popular, and in fact it became so popular that servers increasingly started to become replaced by cloud. So today, if you see, it's very rarely the case that a startup would go buy servers. Most often than not, the startups would be born on the cloud. Over a period of time, as you become bigger, there is still a case to be made that you could look at what's called as repatriation, which means bringing certain types of workloads back from cloud to servers because it's cheaper to do so, right? It gives you more control, it gives you more flexibility, but even that is going to be rather with today's economics in place, it's probably cheaper to do so if you're very large scale. Even at that larger scale, there will be some part of your footprint on the cloud. So all things considered, cloud is here to stay, and cloud is probably your first port of call if you want to start a business, if you want to start to consume a piece of software that's of interest for you. Great. Now let's look at what's happened today, though, right? From a piece of from the perspective of data and software. As cloud became more and more popular, what ended up happening is a lot of the common things that you associate with various parts of the cloud became commoditized. Meaning, I could get whatever type of resource I want at my fingertips, right? If I wanted CPUs of a certain quality, I could get that. If I wanted CPUs of a certain performance, I could get that. If I wanted memory of 16 GB, that's easy. If it's just 128 GB, it's just like a simple click and point, right? Rather point and click. If I wanted GPUs, right? Because I wanted very heavy processing needs, simple, right? So all of that became super easy. But then what happened with software though, right? What was earlier designed to run on servers now suddenly needed to be run on cloud, and cloud had different form factors. So if you needed to be able to sweep completely a set of hardware and replace it with some other set of hardware, the way that software was defined earlier was tightly coupled with the kind of hardware that was running within the servers. Even though the chipsets were general purpose, at the end of the day, it was still controlled by a handful of chipset manufacturers. Effectively, it was Intel, which was doing x86 chipsets, and AMD, which was actually doing its own chipsets at that time. So a piece of software that was designed for x86 could not really operate on AMD servers and vice versa. And if you generalize this a bit more, a piece of software that was assuming certain kinds of hard disk or certain ways of connecting hard disks together, like RAID hard disks as an example, it couldn't really work with other kinds of network attached storage easily, right? So what ended up happening was the softwares had interfaces which were tightly coupled to the kinds of resources that were operating underneath. But with cloud coming into play and cloud becoming popular, software had to be designed that would allow pluggability of different types of hardware underneath, right, based on what the cloud was providing. And even more so, as and when the user changed, right, the kind of hardware, the software had to immediately work, right, not to, it shouldn't be down for any period of time. It should not be requiring elaborate testing cycles to certify that it's able to work on this new hardware that you've provided as an option. Whereas the expectation from the user is, I'm changing the hardware immediately, within 1 hour, within half an hour, within 15 minutes, and sometimes even in real time, the software should just work, right? So in order to cater to those kinds of requirements, the software had to be changed. But notice that it's not the functionality of the software that's required to be changed, but it's the interfaces that it was assuming was necessary for working with the cloud in the backend. So those interfaces became what's known as non-functional part of the software. What I mean by non-functional here is it does not affect the functionality of the software. It only affects the execution of the software. Where is the software executing? What is it assuming about the underlying hardware? So those non-functional pieces started to be engineered separately from the functional pieces of the software, right? And those non-functional pieces became attuned to what was assumed as available from the cloud, right? Or more importantly, what was not assumed. So with the cloud becoming popular, the ways in which you could engineer software to be general purpose and applicable to a variety of different cloud options became possible through an enabling technology called as a hypervisor. One of the first companies to popularize this was VMware, but even otherwise there were other implementations of this that became extremely popular, but those were enabling technologies, meaning if you built your software and if you constructed your non-functional interfaces to work with hypervisors, then you could take it and run it on any cloud which actually supported hypervisor technologies. Over a period of time, this became even more simpler with the advent of what's called as containers. Containers allowed very lightweight execution of units of software without having to go through even hypervisors. So hypervisors had to actually go through extra layers of translation in order to convert your instruction to operate on a disk to the specific underlying disk that the cloud provider was providing. But with containers, those became even more lightweight and became super easy to transport and have portable software working on different types of hardware. So long story short, a lot of work that happened in creating non-functional interfaces that allow software to be truly portable across different settings. So this ability to write software in a way that actually transforms the ability to execute across multiple different types of cloud together created this paradigm of software called as cloud native. So effectively, cloud native is think of it as an architectural pattern which called for creating software which had some very important properties, and those properties, as long as you created software that obeyed those properties, you know for a fact that you're going to be able to have software that will operate very quickly on different types of cloud vendors, different types of cloud environments, can have resilience built in, can have scale built in, can have all the good things related to performance without having to rewrite software later on, right? So this became the foundational building block for startups which wanted to grow at very, very large scale. So imagine you were a startup back in like mid-2000s, like somebody like a Flipkart, somebody like a Myntra. You started off small, you had only, let's say, 1,000 users, and you had software that would do your e-commerce billing, right, or e-commerce shopping exercise. But then the moment you figured out that you could attract a lot of eyeballs, and 1,000 users became a million, became 10 million, then you cannot afford to go back and keep writing new software just because the scale has increased, right? That's where cloud native software became really, really powerful as a architectural pattern. As long as you create wrote software which would be cloud native, you could run it on run it for a base of 1,000 users, but you could easily scale it up to a base of 1,000,000 users without changing the software, right? It would just seamlessly operate on bigger resources, bigger hardware footprint, and nothing needs to change in terms of the software. That kind of a guarantee is possible if you engineer the software with cloud native architectural principles. Now, notice one thing, right? Data that's getting produced by software is actually being produced by both the functional side as well as the non-functional side. The non-functional side of the data is pertaining to things like how much memory did I utilize for the specific operation, what is the current utilization of my cluster, what is the current I/O pattern on my disk, etc., etc. Right? That's all non-functional, and that's useful for optimizing. Right? That's useful for the cloud native side of that software to figure out what bigger cluster do I need, etc., etc. But the functional side of the software is also producing data. That data is actually being analyzed by the business, and that analysis is producing newer changes, right, to the software that is required. Like, for instance, let's assume I'm IRCTC. I have a specific way in which I do discounting, and as a result of the last 1 month of ticket booking that's happened, I've collected the data about the tickets. So basically my software is producing data about tickets, and that data is getting analyzed by my business, and the business comes back and says, yeah, it's Diwali time, it's New Year time, I'm going to change the way that discounts are operating. So I'm going to make discounts very specific to individual regions, right? So for urban population, I'm not going to give discounts. For rural population, I'm going to give discounts. So I come back and say, that's my change. So then some software engineer is going to go back and look at the software which is on the functional side and do the changes that the business is demanding for the discounts to operate, right? So that cycle of production of data by the functional side of the software, analysis by business, and then generating the changes that the business wants to create newer versions of that functional software, that cycle will continue. That cycle continues over, that's been continuing for decades now. So with cloud native, what has happened is the non-functional side of the software and its dependence on the cloud and its independence of the cloud, right? Let's put it that way. That is automated. So now, if you write non-functional part of a software using cloud native principles, you could automatically take it and run it at large scale, run it on AWS, run it on Microsoft, does not matter, right? It just works out of the box, or Google for that matter, doesn't matter. But what has happened is on the data side, as the scale has become bigger on the infrastructure, on the non-functional side of the software has just kept pace with that scale, but the functional side has just produced more and more data, and that more and more data has now required big data tools in order to analyze so that the business can take some action on top of it, right? So in a nutshell, cloud infra and cloud native apps have made scale of operations super easy. So if you're now a startup, you can start small and scale it up super easily. And in fact, the expectation is that you would go from like 1,000 to 1,000,000 like within a week, and nothing will change about how you run your business, right? So that's as powerful as it gets. Data, on the other hand, though, it's still being analyzed by business. It's still being analyzed by data scientists, data analysts, etc., using tools which were traditionally built for small data sets. But as the scale kept growing up, it's necessary to now start looking at big data, right? Big data tools, because that's when you'll be able to truly analyze the data that's being produced by, say, that software that's running at scale. And then that is what the business needs to look at in order to truly do accurate changes that are necessary for it to continue to make progress. So with that, we'll stop with today's with the video on what does it mean to do cloud native software. In the next class, we look at specifics of what the cloud native definition is, and then what are various services that cloud provides in order for you to build cloud native software.